Hello everyone. So welcome to the Geeks for Geeks beginner sheet DSA code along session 3. So in this series, what we're basically doing is solving problems from the Geeks for Geeks beginners curated sheet. And as and when I solve them, I also explain approaches on how to solve these problems using Python. So in today's session, we'll be covering some very important topics that can probably help you along your DSA journey. So just to talk about the problems that we're going to solve today, they're going to be find n by kth node in a linked list, the maximum of subarrays of all subarrays of size k. Then we're going to be looking at a very crucial dynamic programming problem, that is the longest common subsequence problem. Then we're going to be looking at how do you make a queue using two stacks. Then we're going to be looking at another very important problem, which is topological sort. And after that, we'll be looking at the number of provinces problem. And finally, we'll be ending with the Bellman Ford algorithm, which is our shortest path routing algorithm, like the Dijkstra's algorithm that we saw last week. So without further ado, let's just get started with the first problem. The first problem for today is finding the n by kth node. So let me just pull up that problem. Mm, should we go here? Yeah, here it is. So let me just reset the code. Yes. So whenever we see a problem, our approach remains the same as we saw in the earlier sessions. When we look at a problem, first we read the question, and if you're not able to understand how we can approach the problem, we look at the inputs and the required outputs. So let's just quickly look at the problem. Given a singly linked list and a number k, write a function to find n by kth element, where n is the number of elements in the list. We need to consider the ceil value in case of decimals. So this problem seems pretty explanatory. So they have given us a singly linked list containing of n nodes, and they're telling us to return the value at the n by kth node. And if n is not directly divisible by k, we simply have to return the value at the ceil of n by k. So how would that look? Let me just pull up this sheet. So let's say we have this singly linked list containing three elements, right? So n is equal to 3 here. And let's say for the first instance, k is equal to 1. So n by k, which is 3 by 1, we get 3. So ideally, we should be returning the element at 3, right? So if the k value was 2, right? So 3 by 2, we get 1.5, but we should be returning the ceil value of that. So the element at node 2. So how we could approach the problem is actually quite simple. So let me just tell you the approach. So whenever we get this problem, we will take a two-pointer approach, right? So one pointer we will call the target pointer, which or you can even call it head two or head one or things like that. Just for explanation sake, we have one pointer called the target pointer T, another pointer called, let's say, a leap pointer L, right? Just for explanation sake. And we have a K value is equal to 1. And let's say we have N is equal to 3, as in the question, right? Right here. So what happens here is the leap pointer basically at every step it leaps k times, right? And the t pointer for every step it just leaps one time. So a leap pointer leaps k times, t pointer just moves forward one time. And as and when this leap pointer reaches the end of the linked list, we simply have to return the value of the target pointer, right? So how let me just show you here. Just for better explanation, let's take k is equal to 2, right? So first, let's run the whole algorithm manually. So in the first step, as I told you, the L pointer leaps twice. So L pointer goes from here to here. So now this is where our L pointer is pointing. However, our T pointer only moves one step, right? Now, again, what the leap pointer tries to do, it tries to again jump twice. But as you can see, the leap pointer cannot jump any more times. So what happens? It goes out of bounds. So as soon as your leap pointer goes out of bounds, you just have to return the value at 2, right? For example, even if we check like n is equal to 3 and k is equal to 2, we get n by 2, 1.5, we have to return the value at the second place. That is what we are going to return here, right? So this is the basic understanding of the problem, and just to give you a little more intuition how this works. So let's say I'll just write three variables here: k, t, and n. So let's say I'm leaping by 5 every step, right? 5 into 1 is equal to 5. 5 into 2 is equal to 10. So if you have, let's say, the leap pointer, every step, it at every iteration it takes 5 steps, and the target pointer just takes 1 step, if you see, right? So, and even I'll just write this also for more clarity's sake. So if you have the leap pointer jumping at every step 5 times, and you have the target pointer only jumping once. So the leap pointer is jumping k times at every step. So 5, then 5 plus 5, 10, 10 plus 5, 15. And you have the target pointer only jumping once per each step. Then finally, as soon as L goes out of bound, the leap pointer goes out of bounds, you just have to return the value of the target pointer, which will give you the n by kth value. And it's easy to verify also, right? So if n is equal to 5, 5 by 5 will give us 1, which is the value that we have to return. 10 and then 10 by 5, 2, which again is a value you have to return. So let's just quickly code out this solution. So as I said earlier, so we'll have a leap pointer. So leap will point to head and target is equal to head, right? So while we can still leap over some nodes, let's do this. For I in range k, what does the leap pointer do? The leap pointer leaps k times. So this is what this piece of code is doing for us, right? And as soon as the leap pointer goes out of bounds, so if leap is equal to none, so that means it's pointing at the end of the linked list, right? So all you have to do is just return. Should we return the uh, output print the data value of the target dot data, right? Or let's just return. I think before some of input, print the data value of the n by kth. Okay, let's just try returning the target at the start. If it's not doable, we'll just return target.data, target.next, right? So what this is basically doing is what we discussed earlier. At every single iteration, target just leaps by 1, and our leap pointer leaps by k times. So let's just run this code. Perfect. So it runs on the sample test cases. Yeah, perfect. So that is the solution of this problem. So just remember, if you have to return the n by kth node, you need a two-pointer approach where the leap pointer will jump k times and another target pointer will just jump once in each iteration, right? So, and finally, when the leap pointer goes out of bounds, you just return the value at the target pointer or the node at the target pointer. Now, let's just look at the next question for today. So the next question for today is our maximum of all subarrays of size k. We set this as well. Right. So again, our approach remains the same. Whenever we see a question, we read the question, try to understand what exactly they're asking. And if you're not able to understand the question, we just look at the inputs and then look at the outputs and try to make sense of the question. Okay. So given an array ARR of size n and an integer k, find the maximum for each and every contiguous subarray of size k. Let's just read it again slower for us to understand. Given an array ARR of size n, so they have an n-sized array and an integer k. Okay, what does this k do? Find the maximum for each and every contiguous subarray of size k. Okay, perfect. This kind of makes sense. So we have an array which has n is equal to 9 elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And they're telling our window size or the subarray size is 3. And what we're supposed to do for every window of size 3 inside this array, we have to return the maximal element. So let's just look at that. So for the first window, which only has these 3 elements, 1, 2, and 3, we return the max 3. I mean, we put this value inside a list and return it. So we have 1, 2, 3, the max is 3. So we have that in the output here. And again, for when the window slides over, we have 2, 3, 1, maximum is still 3. Then again, when the window slides 3, 1, 4, we have maximum 4, and so on and so forth until the end of the array, right? So this can seems like a deceivingly simple problem. So let me just quickly code out the solution. So return max of ARR of I to I plus k for I in range 0 comma n minus k plus 1. So let me just see what this code does. So the approach is very simple, right? So you just have this. What this code basically does is every single iteration you take a window of size k and you splice out that array and return the max of it. So in the first iteration, you take this 3 to 1, splice it out of the array, get get the maximum of that array and put it to a resultant array, right? So again, in the next iteration, you splice out 2, 3, 1, get the maximum of 2, 3, 1, and put it in a resultant array. So let's just run this code and see what happens. That's kind of strange, right? We have a time limit exceeded error. So this is a teachable moment for us. So whenever we face a lot of read or go through a lot of DSA problems, we also sometimes have to look at the expected time complexity and expected auxiliary space, right? So basically, when they say expected time complexity, it gives a clue to us that okay, this problem, if we have an approach and our expected time complexity is much higher than what is needed, then it's probably going to throw a time limit exceed. So here they tell the time complexity, expected time complexity for this problem itself is just O of n. So what is the time complexity of our problem, right? So what we're basically doing is for every single, almost every single integer inside our list, we are forming a subarray of size k, and we're going through all those subarray of size k elements and then returning the maximum of it. So roughly, our program is almost like O of n into k, roughly, right? It's not exact, so it's a little bit lesser than this, but yeah. So it's O of n into k, right? But the expected time complexity is just O of n. So that is where we are going wrong. So we have to find a better algorithm to solve this problem. So let's just take a look at this, how we can solve this problem in lesser time complexity, right? So let me just quickly go here and clear out my board, right? So let's just take this example itself. So we have n is equal to 9, k is equal to 3, okay, and we have 1, 2, 3, 4, 1, 2, 3, sorry, 1, 4, 5, 2, 3, 6, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So how do we solve this problem? And I'm just going to push it here. To solve this, in order to solve this problem, we'll be using a data structure called a DQ, right? So what does a DQ do, right? A double-ended queue. So a double-ended queue is one versatile data structure that allows you to not NQ and DQ, but add and remove elements from the front of the DQ and add and remove elements from the back of the DQ very, very efficiently, right? So if you have like something like a queue that can, it's a first in first out data structure. So uh, the NQ happens on one side and DQ happens on the other. For the stack, both the NQ and the DQ happen on one side, right? But those are very, very limiting data structures. So here we have to use something called a DQ, which allows us to both NQ and DQ from the front and NQ and DQ from the back. So let's just see how we're going to solve this problem using this DQ data structure, right? So let me just write this DQ here. So just to give some context to how this problem would work is, just remember at every single point, DQ of 0, that means the first element, so DQ of 0 will be our maximal element inside that sliding window, right? So DQ of 0 will be our maximal element inside the sliding window. And whenever we have to append inside the whenever we shift a sliding window, we simply have to add whatever is a DQ of 0 to our resultant array. So let's just look at how we can do this. So for the first sliding window, we have to do a kind of uh, not manually using a loop itself, but for the first, we specially process these elements and then we just use a for loop and slide the whole array. So for the first iteration, just put the So here we're not going to be using the values, we're going to be actually using the index of these elements. So 0, 1, 2, 3, 4, 5, and so on and so forth, right? So just put the index of the first element as is inside the DQ, right? Don't worry about what it's going to do. Now, if now you start iterating over the other elements inside the array. Now, if you have this kind of scenario where ARR of I is greater than equal to ARR of not ARR of DQ minus 1. So then what you do is pop back, pop back. So basically what this means is if ARR of I is greater than greater than equal to ARR of DQ minus 1, pop from back. So what this basically does is just to give you some context, minus 1 means the last element inside the DQ. DQ of 0 means the first element inside the DQ. DQ of minus 1 means the last element inside the DQ, right? So if so let's consider this element 2, right? So ARR of uh, the index value is the I value, right? So if ARR of I, that means if 2 is greater than equal to, what is the last index inside the DQ? 0. What is that array of 0? So that is 1. So if 2 is greater than equal to 1, pop back. So what I'm saying is remove this element. Then after you do this operation, you keep popping elements until this condition holds true, right? If ARR of I is greater than the last element inside the DQ, you keep DQing these elements. And finally, once you have done this, append this index. So we have 1. In the next iteration, do the same thing. So we have ARR of 2 is greater than equal to last element inside the DQ is index is inside the DQ is 1, and the value at that element is value at that index is 2. Now is 3 greater than 2? Absolutely. So you pop this 2, and because there are no elements to pop, so you just put 3 inside the you put the index value 2 here, right? Now we have to shift the whole sliding window, right? Sorry, we have to shift the whole sliding window, right? So what sliding window is here has to go to the next position. But before you slide, what you do, once you slide, what you do is first add that element at DQ of 0, right? So add that element to DQ of 0 to our resultant array. And then if whatever is at DQ of 0, if that index is smaller than what the index is inside the sliding window. So for example, the index at DQ of 0 for us is 2, but 2 is still within this sliding window. So we don't have to do anything. But however, if the element at DQ at 0 was below our sliding window, right? For example, if you had a 4 here, this condition would have happened where the index at the inside the sliding window would have been 0, which is lesser than the sliding window indices under consideration, that is 1, 2, 3. So what we do is until this condition holds, we just pop out those indices, right? So this may have been a tad bit confusing, but once we code, I feel you'll have a better understanding of how this whole solution works, right? So let's quickly get to the solution. So from collections, import DQ, right? So as I said, for the first DQ is equal to, for the first time, don't do anything and just put the 0th index, right? And now we have to process first k block elements, right? So in the first k subarray. So for I in range 1 comma k, so sorry, small k here. So our logic is simple, right? So we say while dq of len of dq is greater than 0, and so here comes our condition: if ARR of I greater than equal to ARR of dq of minus 1, then what do I have to do? I simply have to do dq dot pop, and finally dq dot append I. So this is basically our idea, right? So as long as the new element is greater than the element at the back of the DQ, we just keep pushing out all these things until we put that index inside the DQ. So this is what this piece of code does. Then we go to process K to len of ARR. elements. Now, right. So now this is where the sliding logic will start coming into play for I in range k comma len of ARR. So what did I say? The first, whenever you're going to slide the window, first we have to append max or dq of 0 to our result. So that is basically what we're going to do. So before that, let me just have this result array to result list to store the results. Result dot append dq of 0. Then what we do is we start sliding. Um, the second step we do is we check if the as I told here, right? So if this index, if 0 was the max and we have pushed past that index into the next sliding window, we just have to eliminate it. If otherwise, if the dq of 0 was pointing to something within the sliding window, we don't have to eliminate it. So this is what the following code will do. If dq of 0 is equal to I minus k, then what I do is dq dot pop left. So if that index was before the sliding window, we just pop it, or else we don't do anything to it. Then again we come back to this logic to add the next element into the slide into our dq. We have to follow the same logic that we have followed here. While len of dq is greater than 0 and ARR of I greater than equal to ARR of dq minus 1, then what we do is dq dot pop dq dot append I. Okay, so all we have to do, finally we'll have one element remaining inside the dq. Let's add that also. Once we start processing, so once we reach the end of this array, there is nothing else to slide. So we shouldn't directly exit. We should put the last sliding window's answer into the result, and then we have to return the result. So let me do that as well. Return result, and let's just try running this solution. Okay, so what's happening here for I in range? Okay. So let's just look at where we're going wrong. So it says 2 to 4. Huh. So this seems like a problem with this. So if you remember, what we were doing is inside the DQ, we're not storing the array values, we're storing the index values. So that's not what we need. We need to store the array values, right? Not the index values. So there we have the solution. So let's just run it and check. Perfect. So this problem is done as well. So let's just quickly move on to our next problem. And just to write what we're doing at each step, if index was before sliding window, if max index was before sliding window, pop it. If, so this is the same step, pop back elements as long as new. So this is what this step is also doing. You can probably take a screenshot of this to help you understand why each of these steps are being taken. So I'll just pause here for 5 seconds. So, and then we'll finally move on to the next question. Okay, so let's move on to the next question. So the next question is a very, very, very important problem that we are going to solve. It is known as the longest common subsequence problem. And how we are going to solve is using dynamic programming or the tabulation method. And this is a very, very crucial method in probably many of the harder problems that you're going to solve. Henceforth, it can maybe be a knapsack problem or 1-0 knapsack problem where you use the tabulation method. So if you understand dynamic programming and let's say even a tabulation method, you will be very, very good at solving some of the more complicated problems in the future. So let's just look at the longest common subsequence problem. So yeah, so given two strings our approach remains the same. Given two strings, find the length of the longest subsequence present in both of them. Both strings are in uppercase Latin alphabets. Okay, perfect. So, just to make it clear, what is the difference between a subsequence and a substring? Uh, to formally define substring, you can say a substring is formed by deleting one or more characters from either the beginning or the end, right? So, for example, a substring over here would be something like AB or BCD or GH or even BCD GH. So, uh, but every element inside the substring itself is contiguous. So, for example, we can't have a substring that says BDG, right? It necessarily has to be BCDG. But the difference between a substring and subsequence is a subsequence is just formed by deleting one or more letters inside the string. It doesn't have to be from the beginning or the end. So a subsequence here would be AGH or AD or even ACD, something like that, right? Or even the whole thing can be considered as okay. So even ABCDGH can be considered a substring or subsequence of it itself, itself, right? Sometimes. So depending on your definition, your understanding of subsequence would differ, but that is the main difference between a subsequence and substring. Substring means you're deleting, necessarily deleting from the end or the start, but subsequence will also involve deleting characters in the middle also, right? So in A, E, D, F, H, R, valid subsequence would be just D and R, right? DR. So what we are supposed to find inside this problem is the longest common subsequence. For example, let's look at these two strings. So, okay, if I just consider A and A, this is they can be a common subsequence A and A. Then again, if you look here, D and D match. So AD can be a common subsequence between the both the strings. And finally, we have this H and H. So ADH. So ADH is the longest common subsequence possible out of these two strings, right? So now, how do we solve this problem? Let's just quickly go into the solution mode. So let's say we have two strings, A is equal to A, B, C, and B is equal to A, G, C, right? So whenever we have to solve this problem, let me try writing this as neatly as I can. So A, G, C. So these are the strings representing B, I mean characters representing B. So then we have A, B, C, right? So here basically, if you consider null characters inside B and you consider null characters inside A, obviously there is no common subsequence. So for even the string A, there is null and A, there is no common subsequence. So null and AB, there is again no subsequence, and so on and so forth. So the first row and the first column will be filled with all zeros, right? So let's look at the first uh, block here, right? So the block found when B is equal and A here. So when we consider A in string B, and when we consider A in string A, so when we consider this A and this A, so what is the longest common subsequence that we can form between these two strings? Obviously, I think our eyes, we can even clearly see it with our own eyes. So that longest common subsequence will just be 1, right? Because obviously A matched with A. But how do we formally put this, right? So if these two characters that we have just considered, if they match, so what you do is look back diagonally on top, right? Take that value and add 1 to it. Perfect, right? So we had 0 here, we just added 1 to it. Now let us look at the next part. Here, when we come here, right, we are considering A in string B and AB in string A, right? So now what happens is, if you can clearly see, A does not match with B, right? So what is last here A and what is last here B, they don't match. When this sort of a situation occurs, you look to the top and you look to the left, right? And you put the max value here. So on top of B is 0, on to the left, I mean, on top of this value is 0, on top left of this value is 1. What is the max? 1, right? Again, when we consider A and ABC, the same scenario applies. So we just take the max of what's on top and what's on left here, and we just put 1. Now, what does this essentially mean, right? every single value you see inside the matrix is giving a sub solution to that problem. What do I mean by that? So if you are considering only A, and if you are as a string B, and if you're and if you're considering ABC as the string A, then the longest common subsequence possible between the string A and ABC is 1, which is very clear to see, which is that subsequence, just this A and A. So this is the basic understanding of dynamic programming. So how can I put it in the use of dynamic programming in a better way is, let's say you have to clear your 12th standard exam, right? You're writing an exam to clear 12th standard boards. You cannot directly clear like your integration or differentiation paper. What you'll do is you'll integration differentiation may involve some sort of basic understanding of addition, then basic understanding of multiplication, then basic understanding of exponentials. So things like that. So in your first standard you would study addition, in your fourth standard you would study multiplication, and eighth standard you would study exponentials, and so on and so forth until you reach 12th standard. So this is basically how dynamic programming works, right? It breaks down the problem into very very small parts, okay, and it take finds a solution to those small parts, and then make once I found the solution to a small part of the problem, then I make the problem bigger, then I find the solution to that. I keep making the problem bigger and finding the solution until I reach the initial problem that I had. So that is what basically this problem does. So let's just quickly do the same for everything. Does G match with A? No. So I just take the max here. Does G match with B? No. Obviously, I just take the max of what is on top and left. Again, 1. Does G match with C? Absolutely not. Again, I take what is the max of uh, what is to the left and top here. Again, it's just 1. Now coming here, does C match with A? No. 1. Does C match with B? No. Again, I look to top left and no. Now, does C match with C? Absolutely. So whenever these two letters match, what should I do? I have to look diagonally to the top left and add 1 to it. So I get the final answer too. And this answer is very easy to verify, right? What is the longest common subsequence possible? AC, right? So I'm taking AC here and AC here. So that is the solution to the dynamic programming approach to this problem. So let's just quickly code out the solution as we have always done before. So let's come here. Matrix is equal to 0 for I in range. So what we need a matrix that is for 3 characters in each string. We need a matrix that is 4 by 4. So that means just like 3 plus 1 into 3 plus 1, right? So that is what I'm going to do here for I in range x plus 1 for j. So how many times do I need this for j in range y plus 1, right? So this will basically generate our empty matrix, right? So now let me start filling in each of these blocks for I in range 1 comma y plus 1, for j in range 1 comma y plus 1. So here comes our first condition. If s2 of I minus 1 equal s1 of j minus 1, what should I do? That means both the characters match. I just have to look diagonally to the top left and add 1 to it, right? So matrix of ij is equal to 1 plus matrix of I minus 1, j minus 1. Otherwise, what should I do? Else matrix of ij is equal to max of matrix of I minus 1, j, comma, matrix of ij minus 1. Right, finally I just have to return the bottom rightmost value. So let's just run this. Let's submit it. Sorry, this has to be x. Let's just wait for our code to solve the problem. I think we have done the right solution. Yeah, perfect. So we got our solution to this problem as well. So just remember, take a screenshot of this answer if you need, or you can even take a screenshot of this diagram. Very, very crucial to your understanding of dynamic programming itself. And it's a very, very crucial algorithm to solve very, very hard problems inside DSA, right? So just one, two, three screenshots done. Okay. Now let's go to the next problem, right? So once we have overloaded ourselves with good algorithms, let's try for something simpler, which says print the first, given a number n, find the first n Fibonacci numbers. The first two numbers of the series are 1 and 1. Okay, so I'm assuming what you may know what a Fibonacci series is. If not, it's fine. So the first two numbers of a normal Fibonacci series are 0 and 1. To get the third number, you simply have to add the previous two numbers. So you have 0 plus 1, you get 1 here. And to get the next number, you just have to add the previous two numbers. So 1 plus 1 will get 2. And again, add the previous two numbers, we get 3, then 5 and 8, and so on and so forth, right? So that is what a Fibonacci series is. Here, the only difference is that the first two numbers of the series are 1 and 1, right? So some will start with 1 and 1, then 2, then 3, and so on and so forth, right? So how can we solve this problem? Quite easy. So if n is equal to 1, so I'll just return 1, okay? Because that if there's only one element that they've asked for, you just basically have to return just the first element in the Fibonacci series. That is just a list containing 1, right? Then let me just do this, right? So I'm just generating a list, or otherwise, if n is something greater than 2 that they've asked for, you just generate a list containing 1 and 1, the initial two elements inside the Fibonacci series, right? For I in range 2 comma and you just do res of I is equal to res of I minus 1 plus res of I minus 2, right? Then what you do is just return res, right? Oh, sorry, this I'll have to append rather. Res dot append. Let's submit it. Perfect. So this is how we solve or generate a list containing the first n Fibonacci numbers. Right? But just one thing to remember whenever you're solving any other problem related to Fibonacci series. So sometimes you may have learned an approach to find the Fibonacci value at n using recursion, right? But the problem is when I use recursion, it can get highly time complex, right? It can if the value of n is large and you're using your recursion to find uh, the Fibonacci value at that certain location, if you have a very high value of n, then it's going to be exponential almost the time complexity, right? So never do that. Always use some technique of memoization. That means, again, very similar to dynamic programming. What it says is that you kind of store the result for uh, what we're doing here, right? So whenever I'm trying to find the next number in the series, I already have the previous two results stored and res I minus 1 and res I minus 2. I just simply have to add them. I don't really have to find what res I minus 1 and res I minus 2 are because they're already in my list. This makes it a much more efficient algorithm. So just a reminder, never try to use recursion to find the nth element inside your Fibonacci series, right? Okay, so let's just quickly, we have already solved four problems for today. Now let's just go on to our fifth problem, that is queue using stacks, right? Where is it? Where is it? Where is it? Queue using stack. Okay, so this is uh, quite a self-explanatory problem. We just have to implement a queue using two stacks. So that is stack one, S1 and stack S2. Right. So how might our logic for this problem work? So let me say I have these two tumblers. Okay, two tumblers like this, right? And I have to put elements inside the stack, inside the queue, 2 and 1. So these two tumblers, which are also, why do I, let's say I have these two balls that are named 2 and 1, okay? And why do I consider these tumblers as stacks? Is because imagine you're putting something inside a tumbler, right? So something like this inside a tumbler. So if I'm just enqueuing my first element inside, I mean, if I'm just adding my first element to the stack, first I put it right inside, and then if I have to put some other element inside the stack, for example, first I put my sharpener inside, and if I put my watch inside, right? So that is my second element in the stack. Now I cannot take the sharpener out of this tumbler until I take my watch outside. So this is basically a first in last out data structure, right? So only when I take out my watch, I can take out my sharpener. So this is why I say my tumblers act as two stacks, right? So now let's say this is S1 and this is S2, right? So this logic is simple. So the S1 will simply just handle our NQ operations. So first we get I put my ball 2 inside, then I put my ball 1 inside, right? So now I can't get ball 2 outside until I take out ball 1. But according to a queue, whatever went in first should actually come out first, right? So if I put 2 inside first, inside the tumbler, I should be able to DQ 2 first. So now, whenever we DQ, what we do is take all these elements inside the tumbler and put it inside S2, right? So first, 1 will go inside, and then 2 will go inside, right? So now if you see the situation as reversed, so whatever is on top is the one that I needed to DQ in the first place. So then what I do is I pop this element 2, and then whatever is remaining inside S2, I push it back inside S1. So now we have this ball 1 inside S1. So this is how we are going to implement a queue using two stacks, right? So this is stack S1 and stack S2. So whenever we get elements to NQ, we simply push it inside stack S1. And whenever we have to DQ, first we transfer all these elements into stack S2, pop out whatever is on top, and then push back all these elements back inside stack S1. So let's just look at the. So before that, let me just make a constructor def init self, right? So self dot stack 1 is equal to self dot stack 2 is equal to empty, right? So both stacks are initially empty. No surprises there. As I told, NQ is a very simple operation. I just have to add it to stack S1. So self dot stack 1 dot append X, right? Now DQ. If I don't have any element inside stack 1, that means, okay, I can't do anything, right? I can't DQ anything. So at that time, I just have to return -1. If len of self dot stack 1 is equal to 0, return -1. Else what we do is, first our logic remains the same. Take everything out of stack 1 and push it inside stack 2. So while stack self dot stack 1, self dot stack 2 dot append self dot stack 1 dot pop. Okay, then what I do is remove that element. Once I put everything inside stack 2, I remove whatever is on top of stack 2. So returnable is equal to stack 2 uh, self dot stack 2 dot pop. Okay, now what I do is once I have taken whatever I have to pop outside the stack 2, I push back all the elements inside from stack 2 inside stack 1. So while self dot stack 2 self dot stack 1 dot append self dot stack 2 dot pop, right? And finally I simply have to return returnable. Done. Let me just run this. Says a runtime error. Okay, so this is just something that has to do with this function, right? So let's just run the solution. Perfect. So now we have understood how do we implement a queue using two stacks. Right. Now we come to a slightly more complicated problem, which is our topological sort, right? So we have solved this as well. We've solved five problems, and now we're going to move to slightly more harder problems than we have done so far today. So where is it? Where is it? Topological sort. Yep, right here. Right. So just to understand what topological sort is basically you have this. Okay, so topological sort always works only on directed or cyclic graphs, right? It does not work on, just for you to understand, does not work on cyclic graphs, and it does not work on undirected graphs. So what are directed graphs? So every single edge has a sense of direction to it, right? So for example, if you look at this case here, one has a sense, this edge, right, from 1 to 0 has a direction. It's not undirected. So we have 1 to 0. This edge, we have 3 to 0 this edge, and 2 to 0, and clearly there are no cycles inside this graph, so a directed or cyclic graph. Right. Now, what does a topological sort mean? You simply position all your nodes in such a way that whatever follows, if there is an edge, or for example, if there is an edge that takes you from 1 to 0 inside your graph, in the topological sort, 0 should not come before 1. Right? As simple as that. So if there is a path from u to v inside the graph, that means inside your topological sort, this u to v ordering must necessarily be there for all nodes, right? If and there can be even intermediary nodes. It can be u, v, w, x, y, z. In this scenario, a path that goes from U to Z like this. In this scenario, any node that appears before Z, that means U, V, W, X, Y, Z, in your final topological sort, they can never come before Z. How can I put this in terms of your, like a real world example is, let's say that you're doing um, engineering, right? And there are many courses, many ways to get to engineering. So you could have done ISC in 11th and 12th, you could have done CBSE, you could have done your, and well before that, you could have done your first two, 10th standard, and then 11th and 12th, then you go to engineering. Okay. Now, let us say we have this, in this scenario, right? So we have your, let me call HS is your, okay, let me call middle school MS, right? From MS, you go to your high school, that is your 8th, 9th, 11th, 12th, or even in some cases just your 11th and 12th. Then finally you can do, let's say, engineering, or let us say you can do something like psychology or architecture or medical, so on and so forth, right? Now, in a topological sort, for example, you should always have this rule, right? MS, HS, Psi, and ENG, or it can even be something like engineering and psychology, right? So, see, the order of these two don't matter where engineering and psychology comes, because psychology doesn't lead to engineering, or engineering doesn't lead to psychology, right? Because they are two separate pathways. But there should never be a scenario in which, in your topological sort, high school should appear before middle school, because it's simply not possible, right? So, this is what a topological sort can do. Once you perform your topological sort on this graph, it gives you a sense of direction and how all these nodes can be traversed. So this is our example, right? In no case should psychology come before high school, or psychology come before middle school, or even high school should not come before middle school. That is what topological sort does. So now let's just quickly look at the code to solve this problem. So if you we are going to be solving this problem by using depth first search. If you don't understand, if this is your first session and you don't understand depth first search, it's absolutely fine. You can go back and look at one of session two's videos, where we actually looked at solving problems using depth first search, right? So basically is equal to, so basically what visitor does is just an array of v values, which tells me if a certain node has been visited during the depth first search, right? And finally I'll have this other value called stack. Basically a stack will, what it'll store is my topological sort ordering, right? And if the stack is actually not a special data structure here, it's just the list implementation within Python, right? So what I do is, for I in range v, if not visited, I dfs of I, right? So here what I'll do is I'll define a function within this function. So def of DFS is equal to u, I mean, takes u as a parameter, visited of u is equal to true, right? For v in the adjacency of u. That means for all the other nodes inside the graph that are connected to u, do the following step. If not visited, if not visited v, then dfs of v, and finally stack dot append u. And finally, once we have performed the DFS, when we are returning it, we basically just have to return I mean, reverse the whatever is in the stack and return the topological sort. So how, for example, let's just return the value and then look at how it works. Stack of -1. Right, let me just try running this. Let's say list is not callable. Copy. Sorry, this is not this. It's this. Mm-hmm. Okay, so this works. So let us quickly try and understand how this works, right? And one more thing, just before I even get to the explanation of this problem. So here in Python, right, you can write these functions inside functions that are super effective. For example, in many cases, you would have to write some sort of helper functions, right? So even to call a recursive function, maybe you need like a helper function to give it more information. For example, here when I'm doing this topper sort algorithm, I need this visited array and this stack array or visited array to basically tell me what nodes are visited and this stack to actually hold my result. But the recursive part inside this function is only this much. So in other languages or maybe in other style of programming, I'll have to first have a helper function that will add all this information, and then I'll have to define another recursive function which does the recursive step, right? Here we can write both the helper information and the recursive function itself inside the same function. So that makes it really effective and manageable, right? The whole code. So this is a really nice programming construct that you can use. So let's just look at how this whole thing is going to work, right? For now, let me just consider this graph 1, 0, 3, 2. Right? And our code basically says for I, this part is skipped. Initially, I'm just making a visited list of 4 false values, and stack is also 0, nothing to add on there. Now for I in range V, so what values will I take up? 0, 1, 2, 3. So those are the node values, right? If not visited I, so the first value we take up is 0. 0 is obviously not visited. So what we do is DFS of I. So basically, we just go back and we say, okay, go and find me the nodes that are directly connected to 0 or connected to 0 eventually. Like, for example, 0 is connected to 1 and then 1 is connected to 2. So find all those nodes like in a depth first manner. So what this function does is basically that. Right, first it marks the uh, okay, so maybe this example won't give us a lot of clarity because there is no sense of depth here, right? Every sort of value is just one edge away. So this doesn't give us a lot of information. Let me just draw a better graph for us to understand. Let us say I had some graph like this, right? So this is our stack value, right? So we basically what we're doing first is we come to this zeroth value and perform DFS on it. Okay. So basically, initially all these nodes are not visited. These are all false, right? So first, what I come here and do is I'll just try to maybe pull these two things. How do I push it? That's strange. Yeah. So if this is visible, yeah. So visited of u is equal to true. So first what I do is basically uh, visit this node, right? So it's already visited. Now what I do is for all the adjacent nodes to u. So what are the adjacent nodes? This is our current u. What is our adjacent node to u? That is 1. Okay. If not visited of v. So is this adjacent node not visited? Absolutely. This is the first time we're even looking at it. Then what I do is I perform DFS on this, right? Now I call this DFS function, goes back here. Now u value is 1, visited of u is equal to 1. Yeah, visit this, right? Now what I do is again for all the neighbors of 1 that only we have this neighbor 2. Is it visited? No, not yet. Then I perform DFS on this 2 node. Once I come to this 2 node DFS, I visit it, I mark it as visited. So all these become true, right? So are there any neighbors of you that are not, first of all, there are no neighbors itself. So we don't even have to go to this case. Uh, so we're not going to perform any more DFS. So we just basically have to come here and append the value due to the stack. So this is our 2, right? Again, now this DFS is over. We come back here and there are no other neighbors of 1. Basically append that value as well. Then again, there are no other, we go all the way back here 0. There are no other neighbors of 0 as well. So we append that as well. Now we have 2, 1, 0. But as I told in a topological sort, if there is a path between u to v inside the graph, then u must come before v inside the topological sort. And if you just look at our stack, right, it is just the reversed topological sort. So it's simple. When I have to return my topological sort answer, I just have to reverse this topological sort value and return it. So that is what you see here, right? Maybe my camera is hiding that part. But when I say return of stack colon colon minus 1, basically I'm just reversing the final resultant stack and returning it, which will give me my topological sort value. So that is how this code also works. Maybe you can take a screenshot of this and understand the problem, right? Perfect. We just wait for 3 seconds. 3, 2, and 1, right? So now we have understood topological sort, again a very very crucial algorithm for understanding many more complicated graph algorithms in the future. Again, we saw why it's very important. For example, if you have a lot of courses in the universities and some courses have prerequisites, so you can topologically sort all these courses in such a way that you will definitely know what sort of prerequisites you must complete in order to get to a certain course, right? So you will never be taking courses where you don't know the subject. And I'm pretty sure topological sort is being already used in cases like this in universities and things like that to actually arrange these subjects in a logical manner. For example, you wouldn't analyze algorithms before you even study data structures, right? So data structures are prerequisite for analysis of algorithms. So analysis of algorithms will follow after your data structure. So that is the basic understanding of topological sort. Okay. Now we have understood what topological sort is. Let's look at another very crucial problem. That is the number of provinces, right? Given an undirected graph with v vertices, we say two vertices u and v belong to a single province if there is a path from u to v or v to u. Your task is to find the number of provinces. A provinces is a group of directly or indirectly connected cities and no cities outside of that group. Okay, perfect. So I think this question was kind of self-explanatory, but if we haven't understood, no problem. Let us look at this graph and know. For example, in this graph, right, how many provinces are there, or how many um, disconnected components are there, right? So we have this 1 and 3 are connected, so all of this forms one component, and this component 2 is disconnected from every other component. So this basically forms another single component. So how many provinces are there? Just two, right? So 1, 3 and another component 2. So as you can see, the output is also 2. Now let us look at this example. Very simple to identify. There are only two nodes and both of them are connected. So the number of provinces is just 1, right? So just to give like an example, let us say we have some cities, right? We have Delhi. We have I don't know which. I'm sorry, I'm really bad at geography. I don't know which city is directly connected to Delhi. But let us say Mumbai. In our city, Mumbai, I mean, in our country, Mumbai will be connected directly to Delhi. So then we have Bangalore. Or let's say, yeah, Delhi and Mumbai are probably close enough to be considered connected, and Mumbai and Bangalore are considered to be connected. And then we have another city called Paris, right? Now, basically, how our algorithm will work is first, we analyze each of these elements inside our list, right? So first, let me just consider Delhi, right? And then I see if there is a direct connection between Delhi and Mumbai. Obviously, there is. Then what I do is I assign one capital. So, for example, in India, Delhi is the capital. So, what happens? Mumbai will also point to Delhi because Mumbai is connected to Delhi, right? And Bangalore is not directly connected to Delhi, so we just leave it for now. In our hypothetical country, there are only three state. I mean, three cities: Delhi, Mumbai, and Bangalore. So Delhi is directly connected to Mumbai, and Mumbai is directly connected to Bangalore, and there is another city, Paris, right? So for now, Bangalore is just separate, is just on the side, and we have Paris also, which is on the side. Now we consider Mumbai, right? Now we see if Bangalore and Paris are connected to uh, Mumbai in any way. Absolutely, there is a path going from Bangalore to Mumbai. So what you do is make Bangalore point to the capital city of Mumbai, right? And now is Paris connected to Bangalore? No, I mean Paris connected to Mumbai? Absolutely not. Now we come to Bangalore, right? Now we look at Bangalore and we say, hey buddy, is Paris connected to you? No, absolutely not. So yes, now we are done with the um, number of provinces. Now all we have to do is count the number of connected components. Now how many connected components are there in our graph? Just one and two. So this is how we solve the problem. It's basically like we assign a capital or parent, okay? And for all the components that are connected, we make all these components point to that capital, right? So for example, there is nothing for Paris cannot point to Delhi because Delhi is not the capital of Paris, right? Paris is a separate capital in itself. But Bangalore and Mumbai are somehow connected to Delhi, right? First, Mumbai was connected to Delhi, the capital city, and then Bangalore was connected to Mumbai, and Bangalore asked Mumbai, "Hey, bro, what's our capital?" And Mumbai told, "Bro, Delhi is the capital," and Bangalore got connected to Delhi, right? So that's how this connection of provinces works. So let's just quickly code out the solution to this problem. So we have a very similar approach. So what's very funny about this problem is it has a very similar approach to our topological sort problem, right? So and because we are going to be solving this using our DFS algorithm itself. There is another way to do it called disjoint set method, but that is something that we'll be solving much later than today's session. So for parent is equal to okay. So just think of parent as something analogous to capital, right? So if Mumbai's capital is Delhi, then I can also say Mumbai's parent is Delhi or something like that, right? So parent is very analogous to capital. I for I in range B, right? And for I in V in range V, if not visited, I DFS of I, right? So this is very similar to what we have already done, def of DFS of U, okay? If visited of U is equal to true for B, comma C in enumerate KDJ of U, right? So V is basically the other node that is connected, and C basically is this value, right? 0 or 1. If C is equal to 0, that means there is no connection. If C is equal to 1, that means there is a connection between these two cities, U and V, right? So if C is equal to 1 and not visited of V, okay? So what we do is parent of V. So basically here we are saying at the initial stage, right? Capital of Delhi is Delhi, capital of Mumbai is Mumbai, capital of Bangalore is Bangalore, capital of Paris is Paris. But if I find there's a connection from Delhi to Mumbai, I say, hey Mumbai, your capital instead of Mumbai will become Delhi. So Mumbai's parent instead of staying as Mumbai will become Delhi. So that is what this will do. Parent of V is equal to parent of U. Okay, and then DFS of V. Right. Then finally, I just okay. Before I even show you what that does, let me just show you what the solution to this would be. So basically this, right? DFS of, yeah, sorry, DFS of I. Yeah, so you can see here, right? So what is basically this parent value is giving 0, 1, 0. That means the first and third element inside our original graph are connected. So let's just look at our graph. Absolutely, you see here the first and third element are connected because they are represented by one capital value, and the other value was 2 was just represented by 1 itself, right? So that is a separate value. So now what we have to do to find out the number of provinces inside our graph, we just have to count the number of unique values inside the parent list. So how do we do that is something we can even do something like this, len of set of parent. Okay, so let me just run that. Yeah, perfect. So what does this len of set of parent do? It just gives me the number of unique elements inside the parent list. So that is how you solve the question, right? So now we have solved 7 questions for today. Let's quickly go and solve our final question for today, which is our Bellman-Ford algorithm, right? So again, Bellman-Ford algorithm is very similar to our, I mean, at least in the use case, it is also a shortest path routing algorithm like our Dijkstra's algorithm. But both Bellman-Ford and Dijkstra have different advantages, right? So our Bellman-Ford algorithm basically uh, it then you may ask, okay, so why are we using Bellman-Ford if we have Dijkstra's? Okay, the problem with Dijkstra's is it's not very good at handling graphs with negative weights, right? So if there are some negative weights, it may not even detect. Okay, uh, for uh, okay, for example, let me just give this example, right? So let us say you are at your home, right, and this is your grandmother's house, right? So you are spending some, let us say, some 10 rupees and going to her house, right? And what she does is whenever you visit her house, she's giving you 100 rupees and sending you back, right? Now, what a very smart guy will do, he will keep spending 10 rupees going to his grandma's house, getting 100 rupees and coming back. Then he'll keep getting stuck inside this loop where he just keeps on getting rich. But as you know, we have a real world problem where your grandma does not have enough money to keep infinitely supplying you money, right? 100 rupees every time you visit. So that is the basic problem behind algorithms that cannot find if there's a negative edge cycle inside the graph. So what Bellman Ford does is once it finds this sort of negative, I mean here it's actually a positive edge cycle, but if it ever finds something like this, right? So just to change the notation, let us say minus 100 means you are getting 100 rupees and plus 10 means you are spending, sorry, so this would be something like minus 10 plus 10 and minus 100. So if such a situation exists inside a graph, right? Like basically a negative edge cycle. So uh, the value keeps decreasing, the distance cost keeps decreasing inside the graph. Bellman Ford, what you can do is it can detect these sort of negative edge cycles. So that is the basic advantage of Bellman Ford algorithm over Dijkstra's algorithm, right? So let's just quickly see how Bellman Ford's algorithm itself works, right? So I'll not be going into the details of like each of the steps, so I'll just be considering something very simple. Let's see this. Okay, so initially we are at this location 0, and all the other nodes are considered to be at infinite distance. So let me say from A to B there was this path 1, cost of 1, and from B to A to C there's a path cost of 2, and from C to B there's a path cost of 5. Right. So in Bellman Ford, instead of considering the next closest neighbor, what we do is we even leave out that concept itself of going to each node and then finding the next closest and traversable node and then going there and relaxing edges and so on and so forth. Right? We don't do that. We simply consider the edges. Right? So we have A comma B, which is equal to 1. Then we have A comma C, which is equal to 2. And we have C comma B is equal to 5. Right. So now we here these are our edges, and in Bellman for the difference is we only look at these edges to relax all these path costs. We don't look at our um, we don't traverse each node and then look at the next closest node at all. We just simply look at the edges, the number of edges inside the graph, and we start relaxing the paths. For example, let's just take the first one. If you remember the relaxation code, it was something like d of v is equal to min of d of v, comma d of v, comma d of u plus c. So what does c mean? C is basically our path cost, right? D of u is our so D of V is our source node. D of U is our like in between two nodes. D of V is the ending node. D of U is the starting node, and C is the path cost between U and V. So if from the source node plus if the distance to the source node, I mean to the starting node, plus the cost between the starting node and the ending node, if you add both of them and you get a lesser value than the distance of V, then we basically say, okay, the new distance of V is not what we assumed at the start, but it's actually d of u plus c. For example, if I thought let me say, if I thought the distance to my college was actually initially 100 kilometers, right? But then I know for certain that there's a, let's say there's an intermediate location that's actually just 10 kilometers from my house. And that I know for sure, right? So let's say there's a mall, okay, that between my, so this is my house, this is the mall, and this is the college, right? So I know for sure that this mall is only 10 kilometers away from my house, right? And the college, I initially thought it was actually 100 kilometers away from my house. But there is a path from the mall to the college that is just 5 kilometers, right? So D of U here is 10, and I mean, the cost of the path cost from mall to college is 5. So I definitely know if I first go to the mall, which is I know for sure is at 10 kilometers, and then I take this 5 kilometer path, I'll only have to travel 15 kilometers. So the actual distance to my college is not 100 kilometers, it is rather just 15 kilometers. All right. So this is the whole understanding of relaxation. First, you assume every node to be at infinite distance, and then if you find a shorter distance during your search, you say, okay, that is not what I assumed was wrong. Actually, there's a shorter path to get where I'm going. So that is basically what your relaxation concept is. So in Bellman Fort, what we do is we use these edges, we iterate through each of these edges v minus 1 time. So where v is the number of nodes. Okay. And then we try and relax those paths. For example, our first edge is, so this is 2, so this is this. So we have 1, 2, and 5. So the first edge is from A to B, that is 1, right? So distance of A is 0, distance of B is infinity. So now if I look, 0 plus 1 is, that is 1, which is obviously less than infinity. So B is not an infinite distance, B is at a distance of 1, right? What is my next edge? A to C, which is the value 2. So 0 to 2, right? A to C, D of A is 0, cost is 2. Is this less than infinity? Absolutely. 0 plus 2 is less than infinity. So I relax this path. And I keep doing this for all the edges for b minus 1 times. Now, why b minus 1 time is actually very, very simple. So let's say there are 3 nodes in my graph. the maximum number of paths or arcs between a, a V noded graph. That means the maximum number of arcs between two nodes in a graph which contains V vertices. That means if there are three vertices in my graph, V is equal to 3, the maximum path number of edges can only be V minus 1, which is equal to 2, right? Obviously, it makes a lot of sense because I cannot, in no situation, I can have a path which is contains greater than V minus 1 arcs. For example, even if I have something like this, uh, it's absolutely impossible for me to do, right? Create a path which has more than V minus 1 arcs, right? So that is how this whole algorithm works. For V minus 1 times, we go through all these edges and we relax all the nodes. And finally, after we have done this relaxation of all edges for V minus 1 times, right, we come to our Vth iteration. If in this iteration, if our paths are still getting relaxed, okay, if our paths are still getting relaxed, that time it simply means that there was a negative edge cycle inside our graph. And that time, obviously, if we keep continuing for an infinite times, these paths will keep on getting relaxed and we'll never reach an end. So that time, automatically, if on the Bth iteration also we find the paths are getting relaxed, then we say, okay, there's a negative edge cycle inside our graph and we quit. So let's just quickly code out the solution. So here there is one important constraint. So they're saying the maximum distance to assume is 10 to the power 8. So let me just do that. N is equal to 1e8. Then what I do is first I assume all the distances to be at infinity into v except the source which I assume which I know to be at zero distance from where I am right now. So what we do is for I in range v minus 1. So what we do is we do the relaxation step v minus 1 times, right? So before that, what I'll do is I'll just see sometimes I don't know how these edges are defined inside our okay, yeah, it's given here, right? So 0, 1, 9. So inside the edges, we have this sort of sublist containing three values. The first value stands for u, the second value stands for v, and the third value is basically the path cost between u and v. So that is also easy to tell. So for u comma v comma c in edges, okay, d of v, d of v is equal to min of d of v, comma c plus d of c, right? So this is our basic first set of relaxation steps. Finally, we go to our v iteration, right? For u comma v comma c in edges, if d of v greater than d of u plus c, right? Return. That means there is a negative edge cycle. I return minus 1 or else I just return d. Now let's just compile this and see what happens. Okay, before that, I just have to convert this into an integer. Okay, let me try running it and then I'll just check what happens and let us see. Okay, perfect. So what is happening here is basically it's telling, hey boss, you were supposed to give me this value, one e, I mean 10 to the power 8 or 1 followed by 8 zeros, but you have given me this value, right? So why does this happen when though this is what we usually implement as Dijkstra, I mean Bellman foot algorithm, right? So normally in cases, right, whenever we implement this algorithm, this or even when you're theoretically saying, right, we always say, see, if infinity plus infinity plus constant is actually infinity, so we don't consider infinity plus or minus constant, right? We just leave it as is. But whenever you're using this value 1 e to the power 8, 1 e to the power 8 plus or minus something is still something significant, right? So that is why you got the 999993. So how do we overcome that problem is very simple. If d of u not equal to inf, that's it. We just add this other consideration. If that node u has not previously If there is no path found to node u yet, then don't relax that edge itself. So I'll just do that here also. So should do that here. Now let's run it. Perfect. So that is our Bellman-Ford algorithm. So you can just quickly take a screenshot of this, and maybe if you really need to understand Bellman-Ford algorithm a little more, and like there are lots of other useful videos on YouTube just focusing on Bellman-Ford and Dijkstra's. You can really go through them. But just basic pointers between Bellman-Ford and Dijkstra. Bellman-Ford takes a lot more time to compute than Dijkstra's. But the great thing about Bellman Ford is that it can handle negative edges very well, and it can detect negative edge cycles inside the graph, whereas Dijkstra's cannot. Right? Dijkstra is made for very fast computation, but it can only work on certain types of graphs. That's positive edge weighted graphs, right? So that, I mean, for sure, like if you only have a positive edge weighted graph, Dijkstra's will 100% work. Otherwise, it's questionable. So that is the main difference, right, between these two algorithms. So that's it for today. We have these eight very, very good problems solved. Just to go over the highlights of today, we have the longest common subsequence, which is a dynamic programming based problem, which is very, very crucial to your understanding of harder problems in the future. And then we also had three very, very important problems at the end, which is the topological sort problem, the number of provinces problem, and a Bellman Ford. So we used the depth first approach to solve both the topological sort problem and the number of provinces problem. And finally, when we came to Bellman Ford, we saw its pros and cons against Dijkstra's. Also, even the length of, I mean, the maximum of subarrays of size k, that was also a very important problem in our sliding window approach, where we first tried a brute force approach, but then we realized it exceeded the time complexity, and then we found a more optimal solution. So that's it for today, guys. I'll meet you next Sunday with more problems, and we are probably very, very close to finishing our beginner sheet. Probably is going to take just two more sessions. So I look forward to seeing you next week. Take care.